So this was proposed in the 50s by Hugh Everett III. It's also commonly known as the many worlds interpretation. So again, I'll motivate it from orthodox quantum mechanics and the problems we saw with it. So if you'll remember, the textbook axioms that we looked at involved these 4 elements. The first one was about how psi was a complete description of reality. The third one was about how psi evolves deterministically and continuously if the system is isolated. But the second and the fourth concerned measurements and how systems evolve under measurements. And they both involved indeterministic and discontinuous changes to the wave function. So the idea of the Everett interpretation is basically to maintain axioms 1 and 3, but to eliminate the others. So basically to say that there is no discontinuous change in the wave function. Next slide. And there's no indeterminism either. So that's the challenge. Can you pull off an interpretation of quantum mechanics where you don't assume these things? You just have deterministic unitary evolution, and the quantum state describes everything. So let's go back to the measurement problem, which was what motivated people to modify the axioms. And so we had a scenario where we have spin systems. They're coming out of this oven. They're being measured in a Stern-Gerlach apparatus. And if the evolution is unitary and the quantum state describes everything, then at the end of the day, you have this coherent superposition. And it seems as if the apparatus does not have definite properties of indicating up or down. So the Everettian is going to say, let's imagine what happens to an observer. Now, just to contrast this with another approach we've seen, in the collapse theories, proponents of collapse theory said this is unacceptable to have this kind of state. Why? Because, roughly speaking, we don't see states like this. That this would correspond to seeing something strange in the world, something that we don't see. Seeing a Schrodinger cat alive and dead, that's something we never experience. And so if our theory predicts it, there's something wrong with the theory. The Everettian is going to say, well, let's consider carefully what happens to an observer in this sort of scenario. So imagine that you treat an observer as just another physical system, as we've been doing with the apparatus. So they have some Hilbert space. It's going to evolve dynamically. The hypothesis that a quantum state's a complete description tells me that even though it might be hard to describe what the quantum state of an observer is, there ought to be one. So I'm just going to write it down as some ket corresponding to the observer being ready to observe. The first postulate tells me there is such a thing. And then if I couple the spin to the apparatus and the observer in a natural way, so what do I mean by natural way? I mean, if the initial state of the spin had just been spin up and the apparatus were ready and the observer were ready, then the whole thing would evolve to just this. Up, tensor, apparatus indicates up, observer comes to observe up. So this is what it means to be a good apparatus. You feed in a spin Z, it indicates that. What it means to be a good observer is if the apparatus actually indicates up, then you come to believe that. So I'm just assuming here that a term where it was A equal to 1, B is equal to 0 would just evolve to this. And similarly, a term where it was just spin down that was fed in would evolve just to this. But then by linearity, and we're assuming that evolution is unitary, if I feed in a coherent superposition of up and down, the final state must be the coherent superposition of the evolutes of each of these two terms, which are just these two things. So according to the postulate of unitary evolution, even the observer becomes entangled with the apparatus and the spin as a result. So the question is, what would it be like to be such an observer entangled in this quantum state? Well, it's not obvious. The collapse theorist might say that would correspond to having strange beliefs, having strange observations. But the Everettians are quite clever, and they say there's some evidence that suggests that this isn't such a strange state of mind. Because if, for example, you ask the observer, do you believe something definite? Do you have like fuzzy beliefs about what's going on? Or do you believe something absolutely precise, that the measurement had a definite outcome? Well, you just put in sort of a state of the observer, sort of you can think of it as ready to introspect on this question. And then you say, well, suppose that the spin were up. What would the observer do? Well, if the spin were up, the observer would evolve to this. And then the observer would introspect and say, yep, I have totally definite beliefs. I believe it's up. But if the spin were down, then the whole quantum state would evolve to this. The observer would introspect and say, yeah, I have completely definite beliefs. It's spin down. And so in every term, the observer doesn't say, I have indefinite beliefs. In every term, they say, I have perfectly definite beliefs. And you could even define an operator whose eigenspaces corresponding to believing that there was a definite spin. And you could say that the whole entangled state was an eigenstate of the observer believing there was a definite spin. So it's not the case that the observer has vague, fuzzy notions about what happened. So in each branch, the observer will not report observing anything unusual. Take the case where you have two observers as another example. So now I have both observers ready at the beginning. I imagine that the first observer becomes entangled, and then the evolution continues, and the second observer becomes entangled. And what you find, again, the same sort of argument, you apply linearity. You say, suppose the spin was up, what would happen? Well, both observers would measure up. If it were down, they would both measure down. So in every branch, the observers are going to agree. So you also have intersubjective agreement about the outcome in this sort of approach. Nobody's going to disagree on what happened. So Everett observed these features, and he suggested the following kind of way out of the interpretational problems. So he says, we shall deduce the probabilistic assertions of the collapse postulate as subjective appearances to these observers, thus placing the theory in correspondence with experience. We are then led to the novel situation in which the formal theory is objectively continuous and causal, while subjectively discontinuous and probabilistic. So the way Everett wants to resolve the tension between axioms 1 and 3 about psi and its unitary evolution, and the other axioms about measurement outcomes being indeterministic and discontinuous, is to say that the first two describe what's actually happening objectively, and the second two are just about the subjective experiences of observers living in the universe. So how did Everett describe his interpretation? The original paper is called The Relative State Interpretation of Quantum Mechanics. So he wants to emphasize the relations among systems. So he says that neither the system nor the observer has a state of its own, as it would in the orthodox interpretation, but rather you can talk only about the state of the system relative to a particular state of the observer. So you could say of the quantum state I wrote down on the last slide that the system is Z spin up relative to this state of the observer, observing up, and it's spin down relative to the state of the observer corresponding to observing down. So he says the quantum jumps exist in our theory as relative phenomena, i.e. the states of an object system relative to chosen observer states shows this effect, while the absolute states change quite continuously. So again, it's another way of describing where the indeterminism and the discontinuity appear in the theory. It's in these relative states of systems to particular states of the observers. That's the formal way of describing the subjectivity. So let me say a little bit more about this case. But because my equations are getting very long, I'm just going to abbreviate the ready state of the apparatus and the observer as R, and the different possible states of indicating up and believing up as F plus, indicating down, believing down as F minus. And these up and down states will just be labeled plus and minus. So with that notation in mind, I can tell you about a particular problem that people have talked about in relation to Everett, which is called the preferred basis problem. So we have this interaction between the spin and the apparatus and the observer. It evolves to this entangled state. And we're told that we should think of there being sort of two subjective experiences associated with this entangled state. So, there's one branch of the wave function, you have an observer who believes that the spin is up, and the other branch, you have an observer that believes the spin is down. And so you say, well, objectively, both are occurring, but subjectively, they just see one. And the question is, well, why interpret the different subjective experiences as the ones associated with these two branches? Say you take a different basis for the apparatus and the observer, like this one here, the F plus plus F minus and F plus minus F minus basis. Right? So this is also a pair of orthogonal states. These live in the same two-dimensional subspace as are spanned by these two guys. And I can always rewrite this entangled state relative to this basis. And if I do it, I just find that the relative states for the spin are this and this. So these guys are not orthogonal. I have A plus plus B minus, A plus minus B minus. Only if A and B were 1 over root 2 would these guys be orthogonal. But that's OK. These overall terms are orthogonal to one another because they're orthogonal in the second piece. So you could say, well, what's wrong with saying that there's really two subjective experiences associated with this quantum state, and it corresponds to this term and this term. And so, relative to the observer, the spin is in this state here, it's in this state here. And, the observer is one of these states. But now the problem is that, these kinds of states are they don't correspond to anything obvious. They're like a superposition of believing one thing and believing another. So you could say, yeah, there's no reason to pick out this basis as opposed to this basis. So yeah, how are you going to justify in this approach that observers have well-defined beliefs? So let me ask you, do you see a solution for Everett's interpretation or a way to try to make progress on the preferred basis problem?
I think the only way you can is to just assume there is a preferred basis. Get rid of the problem by just saying there is one. Because I don't know how you can make sense of superpositions like that.
So you're saying find some decomposition that you can make sense of and
claim that's the correct
one?
Yeah.
Okay.
Doesn't maybe your preferred basis depends on the measurement, like your measurement system? Because if you have specific experimental apparatus, it'll only measure the states in a certain basis.
Yes.
And so that will determine it.
Well, here I'm assuming that the coupling that happens between the spin and the apparatus is one particular coupling. So let's say it's measuring Z spin. Okay. So this final state here is the consequence of applying unitary evolution for exactly that kind of measurement to the spin and the apparatus. So there's sort of no ambiguity in terms of what unitary was applied. It's just that even though this corresponds to a fully quantum description of measurement of spin along the z-axis, it's nonetheless true that I can decompose it mathematically in either of these two ways.
Is it environment help to truth out?
Yes, the environment can help to solve this problem. So let's see what we can do using the environment. So imagine that you have some environmental degrees of freedom, perhaps a very large environment. Starts out in some fixed state E0. And then because it interacts with the apparatus, for example, and maybe the spin, it's going to evolve into different states depending on what the state of the apparatus is. And so imagine that it goes into a pair of orthogonal states, E plus and E minus, for different states of the apparatus. That's sort of typical. And you saw an example, a tutorial with spin systems, where the states of the environment of the back of the spins became orthogonal for different spin states of the system. So usually we say of decoherence that you get a diagonalization in some basis of the reduced density operator of the system. So if I calculate the reduced density operator of this guy, it becomes diagonal in the plus minus basis. And therefore, because of this environmental interaction and the fact that it's hard to reverse that, there's sort of no way of seeing interference between those two terms. But that's not quite a response to the preferred basis problem, because the objection that was being made can also be made here. You could say, well, there's another way of writing that same quantum state, wherein, again, you decompose your observer into this basis, and you just ask, what's the relative state of the rest of the universe for that basis? And you can verify that it's these two states. Again, they're not orthogonal. But if you stare at this long enough, you'll realize that these are really the same state, just decomposed in different ways. So the skeptic could say, well, it's still, there's an ambiguity about whether I should interpret subjective experiences of an observer as being one of these two possibilities, or say one of these two possibilities. So how would you respond to the skeptic? I'm curious. So people often invoke the environment to try to solve the preferred basis problem, and I'm wondering how you could respond to the response to that defense. So the critic of many worlds is saying, oh, you haven't solved the problem because I can still decompose the total wave function in this alternative way, and I could still try to interpret it in terms of observers having subjective experiences in these two branches rather than these two branches. And that would give something that didn't accord with our experiences. Yes?
Consciousness?
Consciousness. Okay. Tell me more.
Your consciousness can only follow one branch, so you can only feel one state. Again.
But how do you know that consciousness, so philosophers use this term supervenes.
So that determines preferred basis, so then you can't just arbitrarily, as in, like, in another preferred basis, the interpretation in that basis just won't really make any physical sense.
I see. So you're saying consciousness can be said, a story about consciousness makes sense relative to this kind of basis.
Right.
But there's no sense in which a story about consciousness would cohere according to this basis.
Right.
Okay, that's similar to some views that I'm going to be talking about in a few slides.
Could you, this is again choosing a preferred basis, but could you not postulate some kind of symmetric evolution of your system and then saying that this has to be decomposed into something symmetric times symmetric or anti-symmetric times anti-symmetric?
You're talking about particle statistics type symmetries? I'm not sure. I could imagine running this argument with a number of particles that were all distinguishable. And this sort of argument is taking place in the context of just sort of a general framework for quantum theory. It doesn't presuppose field theory. It doesn't presuppose bosonic or fermionic statistics. So the ambiguity in this decomposition certainly holds for distinguishable particles. And if I were doing, say, field theory and second quantized approach, so all my systems now would be different modes, and they would be occupied or unoccupied for fermions, and might have some number of occupations for bosons. I could still have the problem that there was sort of a natural state corresponding to the apparatus having a definite outcome, and the observer observing something definite in the environment going into something, all in terms of second quantized notation. I would have this kind of decomposition. And then I could rewrite it this way if I wanted to. So, let's say there's one mode that sort of picks out detection. So let's say I have a two-mode system, and if it's occupied here, then that indicates the spin is up. If it's occupied here, that indicates the spin was down. So here would be the left mode occupied, here would be the right mode occupied. But I could also decompose it into coherent superposition of 1, 0 plus 0, 1, where it's a superposition of left mode occupied, right mode occupied, and the other superposition. So even in the context of field theories with bosonic or fermionic degrees of freedom, you have this ambiguity in the way you write the wave function.
So maybe postulate some symmetric dynamics for the evolution of a wave function itself, with no reference to bosonic or fermionic. So this is an extra structure in your theory.
Well, so this is not an issue about how the wave function evolves. We're saying that there's some fixed unitary that couples the system and the apparatus and the environment. the wave function evolves as it does, we're talking about an ambiguity in ways of rewriting one and the same wave function as various sums of components. So the many worlds person says, there's a branching structure. I can write the wave function as a certain sum of terms, and there's particular relevance to that decomposition of the wave function. It's irrelevant, usually in the operational formalism, how you write the wave function as a sum of terms. It doesn't make any difference to the probability you predict. But in Everett, you say, look, there are subjective perspectives corresponding to each one of these branches. Objectively, everything's happening, but subjectively, each branch holds its own observer and their perspective. And so now we're talking about decompositions, and the criticism corresponding to which is what's called the preferred basis problem, is that there are many ways of writing this as a sum of terms. So how do you pick out the one that corresponds to the subjective experiences that we have? Any other thoughts? So one difference between this sort of decomposition and this sort of decomposition is that if you continue the evolution further in time, so let's say I have some more environment, which comes to correlate with these guys, and I ask, what's going to happen to this term alone? Right? So now because it's linear evolution, I can ask, how does this term evolve without worrying about how the other terms in the wave function are going to evolve? They all evolve independently. So I can say, how's this term going to evolve? And what you'll find is that it will, the apparatus and the observer will, remain in the state that they started in. They'll continue to have observed up, show a record of having observed up and believing up, because all that further interaction with the environment doesn't really change that. It continues to just acquire information about the apparatus and the observer in that same basis, F plus versus F minus. That's how typical environments work. Whereas if you look at this decomposition and you say, how would a term like this evolve? You'll find that a moment later, this guy here becomes entangled with the environment. Because the assumption we're making here is that there's a particular unitary that couples the environment to our apparatus. So just imagine a run-of-the-mill apparatus interacting with light and air molecules and whatnot. It tends to carry away information about positions of things, like positions of a pointer. That's how environments work. And so these basis states are well localized kinds of states. These ones are not. So if I imagine the evolution of this guy, this apparatus immediately starts becoming entangled with that new environment, right? And so then if I redecompose the states so that I pick out, the evolved version of this state now, again, will involve a component of this and a component of that. So another way of saying this is the following. If I do this unitary evolution between the apparatus and the environment, and I ask, what would occur if I measured this basis, F plus versus F minus, consecutively? Well, if you get F plus in your first outcome, you're going to continue to get F plus in the future. The interaction with the environment is not going to change what state the apparatus is in. But over here, if I start with this kind of state, I evolve forward, right? So originally, if I do a measurement of this basis, the positively superposed and the negatively superposed basis, I'll get this outcome if this is the state. And then I evolve it a little bit, and I do that measurement again. Now I get randomness. I get either this outcome or this outcome. Because when this guy evolves with the new environment, right, so a term like this will couple to this second environment I'm imagining by becoming entangled with it. So I'm just going to imagine that the amplitudes are equal for this example. And then I can rewrite this as F plus F minus E plus 2 plus E minus 2. All right. That plus a term where I have the opposite superpositions. Like so. Push that up. Oh, too far. So in this basis for the apparatus, you don't have much predictability. If you find it in the positive superposition at the early time, then a moment later, you're equally likely to find it in the other superposition. So that's a big difference. It means that in this sort of branching structure, if I look at the evolution of a particular term, it doesn't have much predictability for the observable that was well-defined in this term. Right? So this coherent superposition is certain to occur at the initial moment and then is just a 50-50 chance. And so that's one major difference between these kinds of decompositions, that what you can say about the apparatus in this sort of decomposition is very predictable. It stays in the F plus state for a long time. Whereas for this sort of branching structure, I have a constant bifurcation. That if I really force myself to try to interpret the observer as having one of these two properties, then that property continues to get randomized in every branch. And so there's nothing I can say. I can't really predict how that property of the apparatus is going to behave over time. So people have proposed this predictability idea as a way of picking out a branching structure. And so, for example, Wojciech Zurek has something called the predictability sieve, where you look at measures of predictability. So, for example, loss of purity of a particular branch. And you try to find the basis in which that purity loss is minimized, and use that to define a preferred basis. Okay, so let me mention that there's a criticism due to Adrian Kent. He wrote a famous paper in 1990 about the many worlds interpretation. And his point was that although there are a lot of stories told about how decoherence might pick out a preferred basis, he really wanted a mathematical prescription or a mathematical criterion. So he says no preferred basis can arise from the dynamics or anything else unless some basis selection rule is given. So Zurek's predictability sieve, which is mathematically precise, find the basis which minimizes this particular mathematical function, the rate of change of purity, is the sort of thing that Kent was thinking of. That's a basis selection rule. And any vague story about predictability or anything else is not enough because we're trying to describe our fundamental physical theory, and so anything less than a mathematical prescription for how I ought to interpret, how I ought to pick out a branching structure for interpretation is not sufficient. So, what do you think of Kent's criticism?
I think it's right. It's linear algebra. Like, operators don't care what basis you put in. So if you're going to single out one of them, you need to have you need to put in something else besides the basic structure, mathematical structure you already have.
Yeah. You could say, the approach here, it's worth remembering, the Everettian wants to say that everything is just dictated by the form of the wave function. So we're trying to eliminate terms like measurement from the axioms. So measurement is going to be understood as just some particular unitary interaction between a collection of atoms that happens to be an apparatus and the systems. And therefore, that's the only stuff you have to talk about. So Kent would say, right, that's the language in which you have to express the basis selection rule. It should be possible, if you give me the wave function, I should just be able to compute what the branching structure looks like by plugging it into some algorithm. Yes?
So you can choose some kind of eigen basis of the time evolution in some way?
You mean, like if there's the whole evolution is governed by Hamiltonian, you mean the energy eigenstates, for example?
Yeah. So that it would be changed.
So that certainly would be a good prescription for picking out a basis, right? Because the Hamiltonian gives you some extra structure. If you want to pick out a basis, you need something. So you can look to the Hamiltonian. The problem is that the energy eigenstates are not going to be the sorts of states that are going to correspond to having definite beliefs. Another problem would be if the initial... So let me think about that for a second.
Isn't it because, energy eigenstates can be degenerate? So you have a
Degenerate.
you have you'd be measuring energy, but the
Sure.
state, you can't specify the state.
So that's true. I mean, the one problem that you'd immediately have to start with is that the Hamiltonian, if it does have degenerate energy eigenspaces, you'd say it doesn't pick out a basis, it only picks out a set of projectors. But you seem to need to pick out a basis. But let's suppose, just for argument's sake, that the energy spectrum is non-degenerate, so you really do pick out a basis. The problem is that the kinds of things we expect to get as the answer, which would be terms wherein there are apparatuses indicating definite outcomes and observers observing them, those stories, those pictures tend to change over time, right? So it's not as if the world we see is a totally static world, and yet an energy eigenstate is something that's completely stationary. So any basis selection rule that picked out the energy eigenstates would be saying, the only thing that changes about this branch is the global phase, and nothing else. But that would be a universe where nothing was happening. So we have to do something different from the energy eigenbasis. I mean, another thing you can say is that the bases that tend to describe the world around us often have things that are well localized in space. And that's also something that's not generic to energy eigenbasis. There is another proposal which fits nicely this desiderata that Kent has, which appeals to the bi-orthogonal decomposition. So you saw this, I think, in Adrian's course, and a little bit in the problems from the first week, that if you have a partition of your system into two parts, then there is a special decomposition of any quantum state for that guy, wherein instead of having a sum over two indices, right? So I can always write some state over AD as a sum over two indices, some coefficients, and then states for system A and states for system B, where these guys are orthonormal bases. But the bi-orthogonal decomposition achieves a decomposition wherein you have just a single sum and some basis of states for A, orthogonal basis, and some orthogonal basis for B, where these guys here, if these guys are non-degenerate, these choices of bases are unique. I can write the state using any basis here, but there's a unique choice of the bases, and they're the eigenbases of the reduced density operators of this guy. So you could say, well, if you have two components, then this is a very special way of decomposing this into a sum of terms. And so maybe you can interpret the branching structure as this structure here into the bi-orthogonal decomposition. The problem is that we don't have a natural way of partitioning the universe into two parts. And as soon as you start talking about three or more parts, you don't have a unique decomposition like that one. So there's no tri-orthogonal decomposition where I can write a single sum with bases for all three. But nonetheless, I mean, people have tried to leverage that decomposition into some sort of proposal for this, particularly in modal interpretations, which I had hoped to tell you a little bit about, but we never quite got around to it. So anyways, that's essentially what Kent wanted. Roughly speaking, there have been a lot of proposals of this sort, but they have all been criticized, and they're not entirely satisfactory. Let me give you what the standard, so most Everettians these days don't buy into this kind of approach. And so I want to tell you a bit about what their response is. But first I'm going to give you one other criticism of the Everett interpretation very quickly. So it's called the transtemporal identity problem. So in addition to needing a preferred basis, you need a notion of how to connect basis elements at one time to basis elements at the next time. What exactly do I mean by that? Think back to the de Broglie-Bohm interpretation. In a sense, the de Broglie-Bohm interpretation solves the preferred basis problem by focusing on position. It picks out position as special. And it says, you write the wave function in a particular decomposition. And in certain decompositions, you'll find that one of those waves is occupied and the others are empty, in the sense that we talked about. And that is relevant to how the particle positions move, only the occupied wave. relevant in that case. But in addition to having a way of prescribing one of the many branches as being, the thing that's relevant for future evolution of the Bohmian particle, we also have a guidance equation which tells us if the Bohmian particle is here at one time, then it's going to be here at the next time. So we don't just say, oh, there's a Bohmian position selected from psi squared at every time. That's not the predictions of Bohmian mechanics, because that would correspond to the Bohmian position potentially bouncing around completely randomly from time to time. We also have a notion of a trajectory, a guidance equation that tells us where the Bohmian position is at one time, given its position at the earlier time. And so John Bell made this comparison between Bohmian mechanics and Everett and says, look, Everett has nothing like that. Even if you solve the preferred basis problem and say, this is the basis in which we should interpret things, you still need to prescribe a notion of trajectories. And Everett hasn't done that. And Bell says, well, strictly speaking, it's okay. It coincides with what we observe about the world. You could say, my perspective is that I live in this branch, and the wave function says that I ought to have memories of a certain set of measurement outcomes having occurred. But Bell says that's different from actually saying that there is a trajectory through those branches such that all those measurements did occur. For example, in a Bohmian theory that had no trajectories, you might also have memories of everything that occurs, but the theory would say that's completely disconnected with what happened a moment ago. The Bohmian position might have been in some totally different branch, and the world actually had different outcomes from the ones you remember. So Bell says that's a kind of radical skepticism about the past. Your theory is saying that you have an appearance that there's this past, but it may have nothing to do with what actually happened in the past. And for Bell, that is too crazy. So he doesn't want to. He thinks that there should be some notion of identity across time in this theory. So now let me give you the response to both this preferred basis argument, Kent's argument, and Bell's argument here. And in particular, in response to Kent, the idea is that, so I'm thinking here in particular of the work of David Deutsch and David Wallace, who are both in Oxford. The idea is that no axiom is needed for basis selection because real things, such as macroscopic objects and worlds, are emergent patterns. So the idea is that that there are many things which we take to be real, but which don't sit there in the axioms of our best physical theories. So there are many things we take to be real, even though they're not fundamental particles, or we don't have any precise criterion for them. And let me give you an example of such a thing. There's a real object that we think is useful, tigers. And so in what sense do we think of tigers as real objects? Well, or how do we make sense of the notion of tiger? They're patterns that behave like tigers, and they have certain explanatory power. But note that they're not directly represented in the axioms. Like if I go to the standard model, I won't find any tigers there. I mean, you're taking the standard model course, you can confirm. And furthermore, the kind of explanation that you get by trying to describe or explain the behavior of tigers in terms of the standard model would be completely worthless. It's in practice completely infeasible, but it's also just not effective at all. And even if you went up to the level of cell biology, you wouldn't really be able to explain the behavior of tigers. If you want to do that, you really have to go much further up to the level of maybe evolutionary adaptation theories and the theory of predator-prey relations and camouflage and all that sort of stuff. At that level, you have a chance at explaining the behavior of a tiger. So the sense in which a tiger is a real thing is really at that level of description, not at the level of the fundamental physical theory. But that doesn't make tigers any less real. So effectively, these guys are positing a notion of realism which is associated with emergence, and there's a nice way of formulating it given by the philosopher Daniel Dennett. So Dennett's criterion is that a macro object is a pattern, and the existence of a pattern as a real thing depends on the usefulness, in particular the explanatory power and the predictive reliability, of theories which admit that pattern in their ontology. So it's enough for some pattern to have explanatory power, to have predictive power, in order for us to call it real.
Excuse me?
Yes?
How could we decide which level is more fundamental?
I think the response is that we shouldn't necessarily have a competition for which level is the most fundamental level. It's more pragmatic. If you're interested in explaining something, like you want to evade tigers, for example, or you want to predict something about the behavior of tigers, then the question is, what's the level that's most useful to you? That's the general statement about emergence and the failure of reductionism for certain concepts. Here, the Everettians are basically pointing out that we have a notion of reality for the notion we apply to tigers, and that's the notion that they think is going to be appropriate for saying that a particular set of branches in the wave function are real in the sense of being preferred. That those branches are the ones that have emergent patterns in them. So they'll say we have all these different ways of branching the wave function, but some of them are actually useful for explanations and have predictive power, and other branching structures don't. So, for example, I was mentioning how if you consider your apparatus in the F plus, F minus basis, then those bases have a lot of predictability. If the apparatus indicates up and interacts with its environment, well, in the future it still indicates up. But if I try to tell a story in terms of this basis, F plus F minus and F plus minus F minus, I find that there's no predictability. The very next moment, it's become entangled with its environment and it's been randomized. And so it's just not a very useful basis for describing things because there's no predictive power.
But
Yes.
this is just a really high-level way of selecting another basis. And they're making the basis selection rule based on the criterion of what they want to consider real.
Yeah, so they're basically saying that it was, they solved the basis, the preferred basis problem by saying, yeah, the preferred basis is the one that has explanatory power, it's the one that has predictive power. However, they say it's not precisely defined in terms of a mathematical rule, it's vaguely defined. And that's okay. So they don't need to fulfill Kant's criterion. Never mind.
So how do you define something as being useful at the level of theory that you don't really have any experiments for example? So how do you know that one description is better than the other in this kind of setting? And specifically, you could look at quantum gravity, for example, where there's no experiments. You don't know what's useful or not.
Well, I think they would make a generic argument that regardless of what field of physics you're interested in, having things be predictable at all is useful, right? So there's certain branching structures of the wave function where you'll find a lot of predictability. So you'll have a kind of quasi-classicality, that a lot of what's going on in that branch will be evolving deterministically and very predictably, and there'll be some story. And other branching structures will just be a mess. Nothing will be predictable. These are the really exotic branching structures that I was talking about. And so they're saying, regardless of the status of experimental tests of some theory or other, it's clear that the highly predictable branches are much more useful than the totally unpredictable ones. So yeah, this is the point that the Everettian wants to say, that the branches that are picked out by decoherence, right? So once we throw the environment in, that tells us that there's certain bases for the apparatus that have predictability and others that don't. So the branches that are picked out by decoherence do admit patterns that have this explanatory power. Tigers would be an example of that. Tigers are also picked out by decoherence as things that have persisting properties and have explanatory power. But these patterns aren't precisely defined. There's no mathematical criterion. And yet that need not detract from their reality. So there's lots of things that we think are real, but we don't have a mathematically precise criterion for them. So you probably agree that mountains are real, but there's no precise criterion for where the mountain ends and where the valley begins. That doesn't bother us. It doesn't make us say that therefore the mountain is unreal. Or the concept of a species. I like this example. That if you think about the Darwinian picture of speciation, if I go backward in time through the generations, eventually the organisms sort of blend into something else. There's no critical mutation at which suddenly the species of tiger is born. There's just a spectrum of things that are more like tigers and less like tigers. And yet the non-existence of some threshold doesn't make us say that tigers are less real. And so the Everettian of this persuasion will say, the fact that we don't have a well-defined criterion for picket branches and it's only vaguely defined doesn't make it any less real. Yes?
We aren't trying to explain tigers, though. We are trying to just talk about quantum particles. Because that's what we're trying to explain.
Yes?
So, I mean, this kind of just sounds like something you would tell yourself about the macroscopic world, and then you feel better about your microscopic theory. But since unless there's a way to relate the two, I don't know. This is the kind of idea I would have if I was wrong about something. I would have a story as to why my answer was right, but I wouldn't have a definite reason why it was right. So that doesn't make this wrong. It just means this is the kind of way I would think if I was wrong about something. When I don't have clear relations between things, I just kind of think it's true, but I don't really know how it's true.
Are you saying it's sort of like folk psychology in that sense, or?
Yeah, I guess you have a bunch of ideas or justifications as to why things might happen in psychology, but if you don't really know or there aren't experiments, it could just be, a bunch of stories, or it might not. You might just be kind of using your bias to determine things instead of actually having a consistent theory.
Let me try to defend this emergence view. So I just came up with this example. I'm not sure if it'll work well, but suppose there's a computer algorithm that's running, and it's playing chess. So you could try to understand that algorithm at the level of, say, the electrons traveling in your computer, or you could say, the way I'll try to outwit this chess program is by imagining the program as something that's playing good chess and trying to beat me, and it has intentions, and it's, I just think of it as a chess opponent, and so I think of it as strategizing and figuring out what good moves are and what bad moves are, and trying to win and all that sort of thing. And by thinking about it that way, I can more effectively play against it than if I tried to think of it in terms of the laws of motion of the electrons in the computer. So they're saying something. Here they want a branching criterion. So here's my untested analogy. I don't know if it works very well, but say there's a computer that's sort of running processes in parallel, and you're kind of sort of trying to carve it up into, there's maybe some different programs running here, but I don't know sort of which electron motions to kind of lump together into coherent stories. But if I say, oh, this one here makes a lot of sense as a program that's strategizing to play chess well, and this here is a program that's strategizing to play some other game well, and this is a program that's doing some other artificial intelligence task. Oh, now I have a branching of those parallel programs that makes sense. And I could come up with other branchings, and if I think about it in terms of electrons, then those other branchings might seem equally valid. But at that high level of description, which in the case of, if you're trying to beat the computer, is obviously the right one to take, this branching structure is the natural one. So that's roughly what they're trying to say here. I don't know if that analogy moves you at all. So I'm trying to convince you that their idea that they don't need a mathematically well-defined criterion in terms of the wave function of the universe and has to be maybe the biorthogonal decomposition or something that minimizes loss of predictability. There are analogs of it elsewhere in science. Okay, let's move on. So the Deutsch-Wallace approach also has a response, of course, to this temporal identity problem. They'd say, well, a pattern is something that can either persist across time or not. And so you can, again, get this vague, imprecise notion of trans-temporal identity just by saying what sorts of persistent patterns have explanatory power and which don't. So you don't need a dynamical equation of motion to go along with your mathematical criterion for preferred basis. They're both inappropriate. You just have this more emergent way of thinking about things. Okay, so I'm going to move beyond the preferred basis problem and talk now about the other major problem with the Everett interpretation, which is the problem with probabilities. So the first problem of this sort I'll call the incoherence problem. And it's basically the question of how anything can meet the description of a probability in this approach, given that we have here a deterministic theory where all possible outcomes occur, and there's nothing to be ignorant about. So imagine a situation where you run multiple different Stern-Gerlach experiments, multiple different trials. So in each case, I've prepared the quantum spin exactly the same way, superposition of up and down for each one of the systems. I have a bunch of apparatuses at the ready, and then I just interact them one by one, and eventually they all become entangled in that standard way. Then if I look at the whole wave function for n of these guys, I can depict the branching structure this way, that at every interaction I now get two branches in the whole wave function, and then whether the first measurement got up or down, branches out depending on whether the second measurement got up or down, here and here, and so on. Okay, so I have all these 2 to the n branches now in the wave function. Yes?
But this gives us the probability.
I'll come to it. We'll discuss it after I've sort of told you what the argument is. So the idea of Everett is to say, unlike a hidden variable model, which would say, like Bohmian mechanics, which would say there's some hidden variable that picks out one of these branches of the wave function as somehow occupied and says what's really going on is this, for instance. And all the others were possibilities, but they don't describe actuality. The Everett says, no, it's not like that. They're all actual, right? It's not that one of them is actual and the others are possible. They're all happening. They're all there in the universal wave function. There are many versions of you in parallel worlds seeing different sequences of outcomes. And you're all equally real, and no one of you has any special status in this theory. And so the question is, everything is going to occur deterministically, so what's the role of probabilities? So there's no sense, you might have thought, there's sort of a real version of you, and it ends up somewhere, and the relative frequency, the probability, or how should I put this? The typical kinds of relative frequencies in these sequences are what you're more likely to see when you end up on a particular branch. Well, that sort of talk is inappropriate, because there's no special you that we could talk about. The other problem that people have pointed out is that because the Everettian wants to say that all these things are happening, whereas normally we would say that seeing all plus outcomes in a sequence of Stern-Gerlach experiments for a long, long time, that would tend to be a disconfirmation of quantum theory. Quantum theory suggests that that should be extremely likely, so if we observe it, we should say that quantum theory becomes incredibly implausible. But you could ask, well, why in the Everett view would seeing all pluses cast any doubt on the theory? Because again, all things are happening in this model, so the theory predicts that there will be somebody who sees all pluses. And so why should that person think that the theory is implausible when they see that outcome? There's no sense in this theory, according to the objection, that person could say that what I've experienced was unlikely. Because it's supposed to happen. They're all supposed to happen. Okay. So let me ask you first. So Ali, maybe you have a suggestion for how to resolve this problem of probabilities.
I think it's like well, those who are in between, they have more chance to occur. So, I mean, well, there are some with all of them pluses, which are rare to occur, and it's a kind of, that build.
So you're saying if you just ask what is the relative frequency of sequences that have, say, fraction 1/2 of the outcomes plus and 1/2 of the outcomes minus, you'll find that those sorts of sequences are represented in more branches than, say, the sequence of all pluses.
So the chance for us to end up in one of them would be more likely.
Okay. And now, when you say the chance for us to end up in one of them, it sounds as if you're sort of there's a real me who's navigating this trajectory, but the Everettian says no. You're in all the branches. So what exactly do you mean by the chance of ending up in one of them? You're going to end up in all of them with certainty.
Well, okay, I'm not an Everettian.
Okay. Sure.
So if you have if you see like your consciousness as being some separate random process, then and you follow this along, it will split over all of them, but you can still talk about one end result if you have it as a separate random walk, and then this argument will apply. I'm not making much sense.
It's okay. I think it's a similar flavor that you want a notion somehow of maybe the relative fraction of subjective perspectives that see one thing as opposed to another.
Yeah.
As opposed to saying, where does the real me end up?
Yeah.
And at any point in time, like right now, because the worlds are orthogonal, you only see yourself in one of the worlds.
Right.
So you have a particular past.
Okay.
So you can talk about which branch you have been following. You can't talk about which branch you will follow, but you can talk about which branch you have been following, and based on that, you can kind of pick out one of them.
So you can pick out one what?
One branch that you have followed out of this entire.
And so I could say, I'll look at. You're saying maybe it's a similar point about if you just ask about the relative frequency of different kinds of subjective experiences, you'll say there will be more observers in this multiverse who look back on their past and see relative frequencies of plus and minus that are equal than there are observers who look back on their past and see all pluses.
Yeah, I guess it just specifically doesn't give preference to any one observer.
Okay. Okay.
And also, I mean, in any probabilistic theory, there will always be outcomes which get the unlikely result. Probability doesn't mean that's not going to happen. Probability means that has to happen sometimes. So.
Has to happen sometimes, yeah, in a long sequence.
Yeah. Right.
But if you sort of look at your historical record, since the beginning of modern science and all the Stern-Gerlach apparatuses that have ever been done, and they've all come out plus, you might say, well, that's consistent with this probabilistic theory, but it makes it very unlikely. The objection here is that in the Everett theory, we should have a different attitude towards that observation. But I take your point. If you say you can talk about the number of subjective experiences that have one sort of relative frequency and the number that have another, you could say that if your particular subjective experience is one of the less frequent ones, then that might make you doubt quantum theory even under the Everett interpretation. So let me. Do you want to make one more comment?
Yeah, sorry.
Sure.
I guess there's two things. I don't know if I like the language of calling. I don't know. This is a separate point, but saying the same me goes to all possible paths is probably incorrect because, or at least is a bad way of saying it because the subjective experience of yourself really only does follow one. And then also, I'm not sure relative frequency is directly okay because you can't say necessarily that each outcome is just as likely as the other one. And that's already assuming a priori that you have a uniform distribution over outcomes. And then using relative frequency one may not be, each outcome may not be as equally as likely. In this case, if it's plus and minus on some particular spin measurement, they might be equally as likely, but other ones could be skewed on other sides, and then I don't think there's a way of explaining why probability should be different weightings.
Okay, let me talk about that. That's an important point. So first, let me frame the discussion by mentioning that there's a response that's been given many times over to this problem, wherein what you do is you try to get these sorts of probabilistic predictions from deterministic predictions. So what you can say is in the limit of an infinite number of these measurements, by the law of large numbers, most of these branches will have a particular relative frequency. And so you can define an operator which tries to measure the relative frequency. And then you can try to prove that the quantum state evolves into an eigenstate of that frequency operator. So then you can say, right, as long as the total universal wave function is an eigenstate of some operator, I can say that that property associated with that operator holds. So then you can say, oh, the property having a particular relative frequency holds. The problem is that if you ask, what's this typical frequency, it depends on your measure over the sequences. So what we've been talking a lot about is a counting measure, where we just say how many of these branches have a particular frequency. And so if we do this experiment where the amplitude is A for the spin up and B for spin down, but we just count branches using a counting measure, then we find that the typical frequency in the limit that n goes to infinity is a half up and a half down. But to get A squared, that's the probability assigned to the spin up outcome. So in regular quantum mechanics, we'd say we expect to see the relative frequency of spin up to spin down to be A squared to B squared. To get A squared as the typical frequency of the up outcomes, I couldn't use that counting measure. I would have to use the Born measure. I would say each of these branches has a measure that's given by the product of the amplitudes all down the trajectory that you follow. So then the critic of Everett will say, well, you've assumed a probabilistic interpretation of those amplitudes to make sense of relative frequencies. You haven't derived it. So you still haven't been able to make sense of a notion of probability, because you can't say it's just the relative frequency of observing certain things. You have to say it's the Born-weighted relative frequency. But then, haven't you just put probabilities in by hand by saying it's this Born-weighted option? Okay, so there's been the argument I've just sort of given. You can find it in a paper by Caves and Shack, where they basically point out that in the law of large numbers, you don't derive probabilities from frequencies. You make statements about frequencies given a pre-existing measure. So strictly speaking, in the law of large numbers, you can say, with measure close to 1 relative to the pre-existing measure, the frequencies will come to respect the relative measure of the different outcomes in a single trial. And so you can't derive probability from frequency, is the claim. And other responses are that, in any case, we really have finite sequences in all experiments, so it's not okay to just look at the infinite sequence. And in any case, this whole business about trying to find something that's an eigenstate of a frequency operator will never work, because the universe isn't even in an eigenstate of us doing the experiments. There's some quantum event back in time. Along one branch, the Earth came to exist, and we all came to be here. And along some other branch, there's no Earth, and there's no Homo sapiens. And so, yeah, I'm not going to be an eigenstate of a frequency operator for this particular experiment overall. So there's a second problem with probabilities. I should basically end. It's just called the quantitative problem. And it's all about justifying that mod squared amplitude that we have to weight by the Born weights. So I'm not going to go into the details of that. I'm just going to skip over it. There's some recent work by, again, David Deutsch and David Wallace that tried to use a subjective view of probabilities. So probabilities are just subjective degrees of belief. And they say in a Bayesian universe where you're thinking about probabilities in terms of decision theory, can you make sense of the Born measure as a notion of probability? And then there's counter arguments. So I'll just direct you to that literature. But I'm going to skip over it today. So I'll end the discussion of Everett by just comparing it to de Broglie-Bohm. So first of all, what the critics of de Broglie-Bohm, proponents of Everett, critics of Bohm, say is that this multiplicity of realities that you find in the many worlds interpretation, a lot of people say that's extravagant. That's a reason for not believing in many worlds. It's already there in the de Broglie-Bohm interpretation. Because you'll remember there was all those empty waves. You know, the ontology of de Broglie-Bohm was the universal wave function and some particle positions. And the universal wave function evolves deterministically according to the Schrodinger equation. So it's all there. Some of the branches of the wave function become empty waves, and they're never relevant for the trajectory of the Bohmian particle, but they're still there. They're part of the ontology. So the defender of Everett will say, look, de Broglie-Bohm has everything that Everett has, plus more in its ontology. So if there's anything that's extravagant in its ontology, it's got to be de Broglie-Bohm, not Everett. And Occam's razor should prefer Everett. The other thing they might say is that that additional structure that was added into de Broglie-Bohm, the particle positions, is underdetermined. We saw all those examples of underdetermination. So it's underdetermined by the observable data. And secondly, it's what spoils the Lorentz covariance of the theory. So again, good reason not to introduce it. Further, they'll argue that macroscopic reality, the stuff we see, is an emergent pattern of the wave function and has nothing to do with the configuration of the Bohmian particles. So they'll point out, for example, that when a particle comes into a detector or into an observer's eye and interacts with the eye, it's the wave function that responds to the wave packet of the particle and evolves and picks up a different pattern. And even if the Bohmian particle is nowhere near the center of that wave packet, the wave function is still going to do its thing, and the apparatus and the observer are going to have a wave function, or the part of the wave function that corresponds to them is going to start evolving in very much the way that you'd expect when an apparatus detects something. Good. And all the Bohmian particle position does is pick out a branch. So what does the Bohmian respond? Well, they'll just say, look, all the phenomena depend on the configuration of the Bohmian particle, not on the wave function. Despite this structure, it depends on the particle being there. And the evidence they cite is, well, some of them, Valentini, for example, is that you can make a distinction between the Bohmian theory with the equilibrium distribution and the one that doesn't have the equilibrium distribution. And so clearly, that there must be some predictive power to the Bohmian positions because these are different theories. The proponent of Everett disputes that argument, but that's sort of where it stands. And then finally, the proponents of Bohmian mechanics can say that unlike Everett, the Bohmian theory doesn't have a problem with probabilities because this Bohmian particle position picks out one of those branches. And when we start talking about the probability of giving it a particular branch, it's very easy. We just say it's the probability that the Bohmian particle is in the support of that branch. And there are no philosophical difficulties with that. So hopefully it's clear that it's not an obvious choice between the two. There's strengths and weaknesses for both. All right, so let me sum up basically short summary of what we've covered in the course. We looked at various different responses to the measurement problem. We didn't really get into quantum logic and quantum Bayesianism because there wasn't time. We saw that there was a kind of distinction, a dichotomy that ran throughout the course between ontic treatments of psi and epistemic treatments of psi. So roughly speaking, the psi epistemic invariable models take the quantum state to describe our knowledge. The approaches we didn't really talk about are also more epistemic in flavor. They say quantum mechanics involves an innovation on what we know about the world, not necessarily how the world is. And roughly speaking, the other options took the quantum state to be real. But there are some caveats there. So we saw, for example, that in the standard approach to Bohmian mechanics, psi squared also described the distribution of particle positions, which you could say is an epistemic concept. Similarly, in collapse models, probabilities were objective. So this is sort of the most ontic flavored of them. In Everett, there was a kind of epistemological flavor because there was the universal wave function, but there was the wave function of a particular subjective perspective. And you could say that wave function is something about what that observer knows, what that observer is going to predict about the future. So you could say, yeah, the universal wave function, that's ontic, but the wave function in a particular branch, in a sense, is more tied to the observer, and so it has an epistemic character. So the distinction is not, there are epistemic elements to some of these other approaches as well. So on this question of whether psi is real or not, a couple of questions. If psi is indeed real, and as it is in collapse and Bohm and Everett to some extent, then how do those approaches explain the success of all those analogies we saw in the second week between probability theory and quantum mechanics, between Bayesian updating and quantum remote collapse, for example? On the other hand, you could say, well, nobody's really proposed any psi epistemic realist interpretation that actually works and reproduces the formalism. So can we find such a thing? So final slide. We talked in the first week about axioms. So outstanding questions. Can we find a particularly simple set of principles from which we can derive the formalism of quantum theory? There are a few on offer already. And do they suggest a way of going beyond quantum theory, perhaps, generalizing it? Can we make sense of non-locality and contextuality? For instance, resolving the tension between there being no superluminal signaling and the fact that you seem to require superluminal causes to explain the Bell correlations. And then finally, we saw all these different interpretations, and the status today is that there really isn't a consensus on which is the correct interpretation. But perhaps there will come a day where somebody either provides a novel defense of one of the existing interpretations, embellishes it so that it becomes more compelling, or provides some alternative interpretation such that we get a consensus. And then you might say that, or a near consensus, that might be the day where we really understand quantum theory. And remember, we had this distinction throughout the whole course between the realist approaches and the operationalist approaches. That distinction, which is sort of a philosophical distinction, suggests that it might be hard to come up with this consensus because people differ in whether they want realism or whether they prefer operationalism. So another question you could ask is just, is that distinction, which I've kind of assumed, valid? I mean, is it really a choice you have to make between these two? Is there some middle ground between those options? And might it be that actually our philosophical preconceptions, which sort of put us into these two pigeonholes, are an obstacle to achieving some consensus and understanding what's going on in quantum theory? So, wow, I'm sorry, I guess I'm only 10 minutes over time because we started so late. So yeah, that's it for the course. It's been a lot of fun. There's one last thing I have to do, which is announce the winner to our competition on contextuality proofs. So yeah, the submissions I got were really interesting, and it was tough to decide who the winner ought to be. So I'm going to give an honorable mention in addition to the main prize. So the honorable mention, which is the prize, there's now two prizes, is a PI mug, and that goes to Ali and Robert and Lenny. I think you were collaborating on that. So yeah, it was an example involving the maps that are not three-colorable. What's that?
I can get 2 more.
Oh, okay. We can always get 2 more mugs. So well done. And then the main prize, which unfortunately I don't have today, but it's going to be a copy of Bell's book, Speakable and Unspeakable, goes to Jonathan for a really interesting example involving vanishing triangular functions. So well done.